I'm going to start. 3, 2, 1. Good morning, everybody, and good morning, Ujaval. Welcome to everybody joining live in the chat room. This is the first session of today's QGIS Open Day. We'll be speaking with Ujaval Gandhi, who's going to be showing us the network analysis capabilities of QGIS. I think we won't be doing like too much question and answer format in this one. It's going to be mainly demo, although Ujaval, feel free to correct me. Sit back and enjoy, and we're going to have a tour de force of network analysis with Ujaval. Welcome, Ujaval.
Thanks, Tim, and thanks for organizing this. Really excited to be here. We have a lot of people watching live, so hello, everybody. It's good afternoon here, but I know people are from all over the world, so good evening, good morning, wherever you're joining from. As we mentioned, we have plenty of time. I'll be covering a lot of topics, and I'll be pausing for kind of taking questions after each topic. So maybe Tim can kind of moderate, and you can, if you have questions, feel free to type them in the chat so we can answer them. I also have a link to this deck that I'm presenting. At the end, I have a lot of resources, so maybe you want to get that and follow along. The format of the talk is I'm just going to go through a whole bunch of demos with data. So ideally, you would pay attention to the talk, watch. If you have questions, please ask them, and you can replicate all of these exercises after the talk ends, and you'll have all the data and everything available to you.
Great. And just one housekeeping thing before you dive in is that the stream may drop at around an hour. I don't know if it's something to do with the way that Jitsi works. But if it does, just stick around. We'll reconnect. It usually takes a minute or two, and then we'll reconnect the stream. So please, stick around to the end, even if it drops somewhere around an hour. All right. Over to you, Joel.
All right. Cool. So let's get started. My name is Ujaval. I run a training academy called Spatial Thoughts. The website is spatialthoughts.com. I also publish a lot of material. Some of you may have seen my QGIS tutorials.com. A lot of the material I'm covering today is already published there. And I also do training on QGIS, Python, Google Earth Engine. I'm also a certified QGIS trainer, so I do certification trainings as well, and we can talk about those later at the end if there is interest. So today I'm going to cover network analysis, and this is a topic that's close to my heart because my master's thesis was actually on network analysis, and I did that in, say, 2003-4 timeframe, and there was no QGIS capabilities there. I ended up using ArcInfo back then, and then a little bit of ArcGIS. And come fast forward, 10 years later, after QGIS 3 was released, I was finally able to replicate my master's thesis in QGIS. And that's when I realized that QGIS has come a long way and is quite mature to handle this kind of advanced network analysis task. And that's why I started learning more about what's possible. And I have figured out a lot of the workflows, how to do network analysis using QGIS. So I'll first spend 10 minutes just covering the basics. Many of you may not be aware of, what algorithms should you use, how does network analysis work. So I'll just give a brief overview of 10 minutes, and then we'll dive right into demos. So a network, to think about it, we kind of you can visualize your road network where you have certain roads and you can travel through them around that. And that's a good analogy, but network is a generic term. It works across different types. You can imagine different types of network, even kind of arbitrary non-physical networks like a social network. And what network is, essentially, it's a set of edges and nodes. And if you think about the road network, the streets are the edges. And when the streets intersect, that's a node. And once you have those edges and nodes, you can have a network. And the edges have typically a direction associated with them. So if it's a two-way road, you have a two-directional edges. You have, which way is forward, which way is backward. You also have a weight, how much is the cost of travel. Typically in a road network, that's a travel time. But you can think of you can associate cost with that edge. As I mentioned, street network is the most common one, but you can imagine for GIS analysis tasks, you have things like transit networks. So you have bus stops, which are your nodes, and the routes between those stops are your edges. You have railway lines and so on. You also have utility network, and this is a big application of GIS, where your GIS is used to manage a lot of this utility networks like water pipelines, transmission lines, fiber optic cables, and all of that. And the same concepts that you're going to learn today can be applied to those kind of networks as well. So what are the kind of problems that fall into this space of network analysis? The first one that most of us are familiar with, all of us have used some kind of navigation device where we say, I want to go from path A to path B, give me an optimal path. And the optimal path could be just the shortest path or the fastest path, or maybe it kind of minimizes certain type of cost. So that's a kind of routing is one of the fundamental problems that we can solve using network analysis. Another set of problems that is where a lot of the professional use of network analysis happens is the nearest facility. And you can think of logistics companies where they want to say, I want to deliver this 1,000 packages, which package goes, which warehouse will deliver to which package, or vice versa. I want to have some facility, I want to direct my, a patient to a hospital, which is the nearest hospital. You might have searched, pizza near me, and that's a kind of nearest facility point where you have a bunch of pizza places and say, find me the closest one, and we'll learn about that. We also have this problem called location allocation problem. And this problem is essentially when I want a new facility, what is the optimal location? And the optimal location could be the one that minimizes the total travel cost for all the people, or it minimizes certain other costs, or it maximizes my coverage area. And this is, again, a very useful problem where, if you're using GIS in a local government or for urban planning, this is an important problem that you can solve using network analysis. Service area analysis is given a facility, how far people can reach that facility, or how far can I deliver within a certain time period. And these are typically called isochrones, and you can do network analysis to figure out those problems as well. And the last one is the route optimization, where you have, I want to deliver X number of packages, I have Y number of vehicles, each has certain capacity, which vehicle should deliver package to which place in which order. And this is kind of a route optimization problem. And this is also a network analysis problem. So how do we find out what are the algorithms for doing this network analysis? The most common and the most widely used network algorithm is called this Dijkstra's algorithm. And this is an algorithm that allows you to find the shortest path between certain nodes while traveling along certain edges. And you can see this animation that's showing how it works. The algorithm works on the graph theory. And you'll hear this word graph a lot. A graph means you take your network of physical network and turn it into this network, a graph of nodes and edges. And once you have that, you can apply this algorithm to find from starting node, which node should I travel along to reach my destination in the shortest possible path. And there's a nice video I found. It explains how this algorithm works. Basically, what it does, from starting node, it visits each node, computes the cost, marks those nodes visited. From those nodes, it computes all the other nodes till it reaches all the destination, and then you have the total sum of the cost that it traveled, and it finds the shortest cost. It's a pretty robust algorithm. QGIS, ArcGIS all implement this algorithm for their tools, and we'll use them in all the analysis we do today. There are other algorithms that are sometimes applied in the network analysis. Another commonly known as the algorithm called A-star algorithm. And the Dijkstra's algorithm is actually a subset of A-star algorithm. But when you have a large network, really large network, Dijkstra can be quite slow or time consuming. So A-star is more efficient, but it can be exact, but it can be also approximate. So if you don't want to exact the most optimal path, maybe the nearest one, you can actually do a very optimal fast optimization using this A-star algorithm. There's also another problem with Dijkstra is that you can only have positive cost. So you can see this as you're traveling along the edge here. Each edge has a cost. So maybe it's a distance or the time, but it can only be positive in Dijkstra. But there are certain cases where you might have a negative algorithm where you'll gain some time or you'll gain something if you travel on the edge. So that will be a negative weight. And there's another algorithm called Belbin-Ford that can deal with negative costs. Interesting application of BELP-IN4 I've seen nowadays is kind of in electric vehicle charging. So if you have an electric vehicle, you can get a path where if you take this path, maybe there's a charging station on the way and you'll gain some battery life if you take that. So you can kind of see that's a kind of a negative cost problem. And if you have the slides in the notes, I put on some research which shows how to apply that. So one of the things that you commonly have to deal with is that how do I turn my network of lines, which we typically use in a GIS, to a network? And to turn this into a network, we need to build something called a topology. Topology just means relations. That means the edges have to be connected properly. The nodes have to be at the right place for the network to work. And if your network has, if your road data set or the pipelines data set that you're working has some topological errors, that can cause problems or give you wrong results. And there are common errors, for example, dangles. Imagine a T-junction where you want to have a road that's meeting another street segment, but it's not connected exactly. Just a slight gap there, and when you run your routing algorithm, it will not be able to turn, and your routing will fail. So those are the kind of things that are called dangles. You have duplicate nodes, pseudo nodes, and all of this are problems that can be fixed. QGIS has many tools to help you fix that. There's a tool called Topology Checker that comes as a built-in plugin. There's also a Geometry Checker plugin that can do this. There's also a GRASS tool called v.clean that can clean network topology. I'm not going to cover those in detail, but if there are questions, I'll do some demos at the end of the talk on that. So you take your polyline data, assuming there's got a good topology, then you can start running your network tools on them, and then you can do solve the network analysis problems. So let's dive in. I'm going to demo routing. So we're going to take a road network, publicly available road network, and see how we can route from point A to point B, and what are the things that we need to do, and what are the tools in QGIS. We'll do the nearest facility analysis. We'll take 1,000 address points, and for each address, we'll find the nearest health facility. We'll do a location allocation problem. This is really exciting. I've not seen any examples of QGIS being able to do this, but it can, and we'll try to optimize, figure out which is the optimal new facility for waste management for a city, and this also using open data sets. We'll do a service area analysis, and this is using OpenStreetMap data. A lot of times you say, I don't have my own network. You can just use OpenStreetMap. Network can do routing on that. We'll not do route optimization because that requires a bit of coding, and it is a little more involved, but I have an example and scripts that I'll point you to, and we'll discuss more if there are questions or interest on that, and I'll point you to resources over that. And at the end of the slides, the resources, I'll come back to that and show you that. But so that's all for now. Tim, if there are any quick questions, we can take them now. Otherwise, I'll just dive right into demos.
Yeah, I think you can just keep on going, and then we'll gather up any questions for a little bit. There were some questions about getting the presentation as a PDF. You did mention you're going to share all the resources later. Yeah. So yeah, if you would just remove the little sharing bar at the bottom before you get going as well. Thanks. Okay.
All right. So let's look at this data set. So this is a data set for Washington, D.C. In the US. I like the data portal. I downloaded the data set from the Open Data Portal. I'm just going to share the link. Just give me a second. So this is the where I downloaded this data set from. This is the Washington, D.C. Open Data Portal, and they have a really nice wiki which explains how this data set is structured, how it's maintained, and how a GIS user might use it. So there is a wiki link here which explains the different attributes and how the data is structured. So you can explore that. But this is a street network. It comes as a shapefile. All of you have seen this kind of data before. And the nice thing about this data set, it's a routing data set. That means the data is organized as a block level lines. You can see each road is split into segments which break at each block. And that means at every intersection, there's a separate segment. And this is good for routing because typically at an intersection, you can make turns, you can you can do all this kind of routing along that. If you just had a single line which doesn't break at the intersection, your algorithm will not be able to do it. So there's a structure that if you don't have your data set in the right format, there are tools that allow you to kind of create this kind of structure. But that's why we are using this block roadway data set, and this is used for routing. For routing, the things that we need are our network, but also we need some attributes. We need to know in which direction can we travel on the street. So if I just look at a segment here, and you can see there's got a lot of attributes, and there's an attribute called summary direction, and that shows in which direction can you travel on the road. There's an attribute called BD, says both directions. So it's a two-way street, but if there are one-way street, they have different attributes. So the first step I want to show you is that how do we visualize the different directions of the street? And this is something that is useful to see and validate your results and see how a network looks. It's not required for doing the analysis, but it helps to see your results. So first, let's just style this data set in a way that we can see all the one-way streets and the directions. So I'm going to open the layer styling panel from here. There's already a symbology here. So I'll just create a rule-based symbology because I want the new style that I'm doing to be applied only to the one-way streets. So I'll just add new rule from here, and I'll apply the filter saying that select all the road segments which have the directions. And if I look at this attribute, you can see there are 4 different values. BD is both directions, IB and OB. So if you think about a street, it's got an implicit direction. There's a start point and an end point. So when you're digitizing the data, you start at a node, end at a node. And that's the default direction of the line. And what OB says is that this is a one-way street outbound. And that means it's a one-way street in the direction of the line. So whichever direction is the line, that is the line of travel. That's the direction you can travel when you are traveling on the street. And IB is the opposite. It's that you can travel along the street in the opposite direction of the line. So I can just select all the street which are either OB or IB. And this is a SQL kind of syntax here in the expression. We can say if the summary direction field is either OB or IB, select those. And I can turn that from simple line to a marker line symbology. And you can now see all the one-way streets have this red symbol now. I can say, just put this point on the center point of the streets. And then instead of a circle, let's just do a triangle. So now you can see I have an arrow that is pointing in the direction of the line that is there. So that's only there on the one-way streets because I have this rule that I've specified here. And this is cool. You can now visualize the direction, but it's not correct because this is true only if the line that has attribute OB. If it's IB, that means the direction of travel is the opposite of the default direction of the line. So how do we style that? And fortunately, QGIS has this really nice thing called data-defined overrides, where you can apply some expressions on different styling attributes. So here I can say I have the symbol, and if it's OB, don't do anything, just keep the rotation 0. If it's the opposite direction of travel, rotate the symbol by 180. So I'm going to click this data-defined override here, and I'm going to enter this expression. So if summary direction is inbound, rotate it by 180. And now you can see certain directions flipped. And now you can see all this roads are symbolized correctly. And you can see that if there's no symbol, that means a two-way street. If there is a direction triangle, that's pointing in the correct direction of travel of that. So now let's do some routing. Let's see how this works on the routing. So I'll just have selected a few points you can show. So let's do this one. And just make this a little bigger. So you see these 2 points, 2 bullseye here. So I want to go from this point here to this point. And you can see from our symbology that though the shortest path might be this, you can't really travel, because as you come here, this is a one-way street. You can't turn left here. And so what's the optimal path? Maybe it's going around here, or maybe it's going like this. I don't know. We'll let QGIS figure that out for us. But the important part is that it needs to respect the network rules that it's there, right? So how do we do routing? I'm using QGIS 3.16. This also works in the current LTR 3.10, but you should start preparing to switch over to 3.16. It's going to be LTR in a very short while. So in 3.16, you have built-in network analysis tools, and that's true for 3.10 as well. So I'm going to use this tools under network analysis. It's called shortest path, point to point. So let me just open up the tool. The tool says, where is your vector layer representing network? I can say this is my roadway network. What type of path to calculate? Shortest or fastest? We'll do shortest now. We'll come to fastest in just a sec. We'll do a shortest path. Let's pick a point. So I'll pick a point. So this is my start point, and this is my end point. Okay. And there are some advanced parameters. We need to configure that because we need to tell what are our network constraints. And the constraints are that the summary direction, it says what's the value for forward direction. Say you can travel only around this outbound value, and the backward is IP. And we can leave the rest of the parameters like this, and I can run this. As I run this, you can see what's happening. The algorithm says it's building graph. And now you're familiar with what is graph. It's taking our line network, line data set, and turning it into a graph with nodes and edges based on the constraint that we have given. And that graph will know if I can travel from node A to B based on the constraints we have done. And once the network is built, you can route it. So the building of the network or the graph is the most time-consuming part. Oops, there is. We try this again. Start point, end point, OB. I'm not sure what was wrong. This works. I tested this. If you can spot what's wrong, do let me know.
While it's running Ujaval, does it snap to the line automatically? So if you click the start point slightly off the line, will it make a difference?
No, I think it should snap to the points. No, let's see if this works. Yeah, so this one, I think I just made some mistake. So there's a shortest path that the network figured out. It's not clear because the line is getting merged. But let me just pick that. And you can see now this was the path that was found by our tool, and you can see now this is the shortest path on this network, where it didn't pick this path, though it might be shorter because it's not along our network. And now it found this shortest path, and this is using the Dijkstra's algorithm. So you saw the basic route finding technique of how do we configure this network, and then now we'll start applying those in a larger scalable way to solve more realistic problems. And in the step-by-step instruction, I also kind of take these 2 points, plug it into Google Maps, and it's the exact same direction that Google Maps also gives. So you have your own routing engine now at your disposal, at your desktop, and you can do routing if you wished based on that. Let me show you another example of just routing based on speed. So I've picked these 2 points here, and let's say I want to travel from here to here. But before that, I just want to add some labels to this layer, where I'm going to label them using the speed. So there's a speed limit attribute. And you can see now there are speed limits. This is 20 miles an hour here. And you can see the shortest path is probably this one. But here, this road has a higher speed limit, so you can actually travel faster. And this might be the fastest route. So it might be true. we can try that. So we'll run this algorithm and see what it gives you. One thing to be aware of is that the network analysis tools in QGIS, they work in metric units, so the speeds need to be in kilometers per hour. So to do it right, we'll convert this miles per hour into kilometers per hour before we actually start our operations. And it's typically also a good idea to use a projected CRS in meters, so you don't, all this works properly. But here, at least, I'll show you how to convert those speeds into miles, from miles per hour to kilometers per hour. And there's a handy thing in QGIS. Many of you may not have used it. One way to do this is just to use a field calculator and say add one more column that reads the speed limit, multiplies it by 1.6, and you have your speeds in kilometers. But I don't want to change my source data. My source data is a shapefile. It's, it may keep changing. Maybe I'm reading from a database. I don't want to change my schema. So QGIS has this really nice thing called virtual fields. So I can add a new field to my data source, but it doesn't update the data. That it adds a new column, but that's saved in your QGIS project. And so it's a really nice way to leverage this, add a new column, but without changing the schema. So I'm just going to use this field calculator here. And you can see there's a field, let's say create a virtual field, and I'll just say speed kmph, and I'll pick my field called speed limit, and I'll just multiply it by 1.6, and it's going to create a virtual field here. And now and you can use that virtual field just like a regular field in all the operations. So I can say style it now by kilometer per hour speed. So now you can see my speed is getting displayed in the right font. Maybe I'll increase that so you can see. So now let's do routing on this points and see how that works. So I'll use the same algorithm, shortest path. And let's do the shortest path first. So I'll pick this one. I'll pick the second one. Same thing, some redirection. And there's an additional parameter called speed field, and that I'm going to pick as the kilometer per hour speed. When you do shortest path, it's going to ignore this field, but we'll come back and do the fastest path. So let me just run this again. So again, it's building that graph. In a typical production scenario, or when you're doing this large amount of computation, you don't build graph for every query. You just build the graph and run your computation, and you build a graph again when your network changes. And typically, if you see any services that provide you directions, they'll typically build the graph, once a day or once a week, whenever the data changes. So because this is a compute-intensive operation, you don't want to do this for every query. So now you have the shortest path. Remove this one. And let me just dial this. Right, so this is the shortest path. And it makes sense. This is the less distance. But now let's just come back to the same algorithm. I'm just going to change this from shortest to fastest. Everything else remains the same. And let's see what my algorithm finds. And what's happening here is that the Dijkstra's algorithm is setting the weight of the edge to be the travel time, not the distance. And it's going to optimize the query for reducing the total travel time. And that's why we need the speeds and the amount of distance between the two nodes and the speed that you can travel. It's going to optimize for that, and it's going to give you the fastest path. And you can see now this one, the new one that came up. This is the fastest path. And you can see it makes sense. You can travel faster from here to here. So that's the basic concepts around how to do routing. Maybe you can do shortest, fastest, and you can kind of play around with that. The fastest, the field that you use for the fastest route may not be speed, it may be some other attribute, and you want to minimize the cost, and the cost could be anything. So you can use that in a slightly different context as well. All right, so that's the first part. I'm going to now move to showing you how to do a nearest facility analysis. But before that, I want to pause for any burning questions people may have.
Thank you, Ujaval. Yeah, we have some questions from the audience. The first one is from Andreas Neumann. He asked if the results of the graph building can be cached so that the root finding would be faster in subsequent runs of the analysis.
Yeah, I think it could be, as I show you the next tool that's part of the plugin, and that basically it just builds a graph and then runs thousands of queries based on the graph for that. But I think it'd be a nice option to say, in a single queries like this, right now it just builds a graph again. Maybe if there's an option to kind of say reuse the graph, it can be done. And I think the Python API provides a way to kind of have the graph, and so you might save it to disk and read it again. But yeah, I think for most of the tools that we'll use in, we don't typically do this point-to-point direction in GIS analysis. This is just for a quick demo if I wanted to do it. But if you're doing this kind of more large-scale analysis, that's the tools typically take care of that.
Mm-hmm. Thank you. And then Robin Lovelace asked on Twitter whether it's easy for this analysis to be scripted so that you could, for example, run it from the command line later.
Yeah, of course. So this one, I'm showing everything I'm showing goes through processing toolbox. So that means if I go to my processing history, you can see the tools that I just ran. And yeah, this is the command line that you can run either through your Python console, or there's a now new processing tool, desktop command line tool, which you can run the same command. And you can, if you want to write some PyQGIS script, copy paste this command, and modify this to use this. So because it's going through processing interface, it's just much easier. And if you want to take it one step further, for example, you want to build a network using some fancy constraints, you can actually use the network library, network analysis library that PyQGIS provides. So you can actually do all the low-level network building and routing yourself instead of relying on the tools. But the tools are really great. I've scripted them, just open Python console, paste them, and just do a for loop to just iterate in a bunch of those points.
Thank you. And then the last question, I guess similar vein from Richard Stanek. Is there any possibility to save the graph in QGIS on disk and use it for other calculations?
As far as I'm aware, it's not. I did play around with this, the Python API, and I could get the graph and I could save it, I think, as a blob or a Python blob and read it. I think that kind of works, but there's no standard format that QGIS says it out to. That's something that I've not explored, but should be possible. But as I said, you typically don't need that, and maybe it's a bit clear after we do the next exercise that you typically, when you run the analysis, you just build a graph and do all your queries, and then you're done.
Sorry, and there was one more question, a couple more questions just coming in at the last minute. So the other one was, can we take the results and put them on the web as GeoJSON?
Sure. This is just a line string that you get out, so you can save it as a GeoJSON and put them out. I think this QGIS is a desktop. What I'm showing is a desktop tool, so I don't think you can run the same tool and do a live query on the web. But I think if the QGIS server has supports the processing plugin, then through that you can possibly trigger the same tools.
And maybe last one for this question round. So from GPS Brianza, Brian ZA, I don't know. How can we set the process if we need different costs for time or speed, etc., for different directions?
Yeah, so I think there is, right now it supports only a single cost per edge. The built-in tools do. I will show you some advanced tools that you can use, which supports all these different costs. And it's a good question. For example, what if even in this data set there are different speed limits? So speed limits when school time is on, and speed limit when there's no school. Like, how do you configure that? How do you incorporate current time? And the built-in tools don't do that. If you need to do it, there are solutions that are open source, such as PG routing. There's OSRM. All of the tools will allow you to kind of configure this in much more detail. So we'll talk about those tools also later on.
Okay, thank you. I think we can stop with the questions for now, and we'll, when you're ready for some more, I'll bring them up again. Thanks.
All right, great. So keep question coming. I like to keep my talks interactive. It helps that you've taken out this time from the schedule to be live, so might as well make use of Peak Live and make the session interactive. All right, so let's move on to the second set of problems that I want to talk about. And this is where, I don't want to do point-to-point direction. I want to find, I have a whole bunch of points. I want to find the nearest facility to that. So this is the nearest facility analysis. And just to give a context of the problem, here is the same Washington, D.C. network data set. And I have about 1,000 addresses in the city. And the Open Data Portal has all the address points in the city. But I've selected a subset of 1,000 points. And then there are some health centers, which are, I've selected about 13 health centers across the city where people can go and seek help. So now I want to find out that from every address, every home, which is the nearest health center. And again, this problem can be kind of, it could be anything, could be any facility, could be any place. And we'll see how that kind of problem works. So how do we solve this problem? Here, we know how to calculate direction from up one point to a destination. So I can compute this, but it may not be the shortest path. It may not be the fastest path. I don't know which center would be closest. Say take this point. Is it closer to here via network or closer to here? I don't know. So I need to compute the distances to every facility and then pick the one which is the lowest cost to that. So that's why this is called a distance matrix analysis, where you have 1,000 points, 13 destinations. We'll compute 13,000 pairs, where we'll say from every point, we'll compute the direction to every other point. And then once we have that, we can just pick the minimum. So that's the distance matrix analysis. If you use any of the web APIs like a Google Maps API, they provide this distance matrix API. And I know that this is one of the widely used APIs by logistics companies. And Amazon, for example, would use such services where they're trying to determine where should your package go, and they'll just do a distance matrix query to a web service like that. And most web APIs, here Maps or Open Route Service, all of them provide a distance matrix API. So very popular kind of analysis, and QGIS also has capability to do a distance matrix. To do this, we're going to use this plugin called QNeat3. This is a really nice plugin. I've used it a lot. This is quite a mature and robust plugin. It adds a lot of new network analysis capabilities. So once you install this plugin and you open your processing toolbox, you'll get a new set of tools here under the QNeat3 folder. And these are all the processing tools. So again, same thing. If you use this, you can continue. You can use them in your model, script them. All of that can continue to work. But before we dive into network analysis, I want to show you why such analysis is very valuable and why this kind of analysis is very important. Say you want to do this in a naive way, where you can say, let me just find the closest facility from each point based on a straight line distance. And if your problem is not to travel along the network, that's fine. And I've actually used this kind of a thing in many different analysis, where you can just say, I have a set of points from one layer, give me the closest point to the second layer. So I want to show the tool and also compare the results with what network analysis gives. I search for hub. There's a tool called distance to nearest hub, line to hub. And this is a really nice, simple tool. It says, give me your source point layer, which will say, I want to travel from my address points to the mental health facilities. And I'll say, give me the units in meters. And if I run this, it's going to, for every address, it's going to find the nearest facility by the straight line distance. It's going to ignore the network completely. And you can see this works. You can see now I have, visually you can see this is connected all the addresses to a nearest health facility, and this works. But you can see the problems here. Look at these points. Take this point. It says the closest facility is here, but you can see there's a big park here. You can't travel through that. So you'll need to go all the way here and drive here. So this is much longer than just connecting to this one. So again, this doesn't work. It's a simple analysis, but it breaks down where you need to use a network cost. And the analysis that I'm going to show you will actually do the correct thing, and it's going to find the shortest path to the hub, to the health facility along the network. So I'm going to turn this off, but it's useful to have this as a comparison. All right, so let's do this analysis. We have the QNeat3 plugin installed, and I'm going to expand this, and there's a distance matrix tool. There are a bunch of tools. We'll use this one called OD matrix. OD stands for origin destination, and we're going to do an OD matrix from layers as lines. it's going to ask if this tool is very familiar to the built-in network analysis tool. It just builds on top of that and gives you some additional functionality. So the network layer is the roadway block layer. The from point layer is the trace point. So these are the 1,000 points. So if I want from each of those 1,000 points directions to all the destinations, and it needs a unique ID, just so that in the output layer you'll get those points referenced by this unique ID, and so you can later join the attributes using that field if you need to. And the 2 point also has this object ID. And then we're going to do optimization using shortest path. There's a new thing called entry cost. And this is important because you can see each of your address points, they are not on the network. So they need to be snapped to the network, or there should be you need to travel to the nearest edge and then do the network. So that is a cost. So that's a distance. So how do you want to compute that distance? And you can, the default is ellipsoidal or planar. And we have our data in our geographic CRS, so we'll use ellipsoidal. If you are using a projected CRS, you can use the planar calculation. Direction field, we're going to set the same direction field here. So it respects the one-ways while doing the routing. And another important parameter that we need here is this topology tolerance. And what happens is, in this case, there are certain points which cannot be, because of where they are located, you cannot find any route to any destination because it's not possible to do that. Maybe this data set also contains some mistakes where there are certain gaps in the layer. So you can specify a small tolerance. So when it encounters some topological error or there's a gap, it will assume that, okay, if there's within the tolerance, I can jump that gap and still continue routing. So I'm going to do a very small one. If you specify a large one, what will happen is if there are real gaps in your layer where it'll jump from one street to the next street because it thinks that's part of the tolerance. So make sure you keep it small. Ideally, you start with 0, see if some of the points fail, and then increase the tolerance. So I did a bit of trial and this kind of works on this one. So if you're using in meters, I typically use like 10 meters or 5 meters as a tolerance. It's a good enough tolerance to overcome minor errors there. And when you click run, what is going to happen is it's going to build the graph, and then it's going to run 13,000 iterations of the direction algorithm on this 1,000 points, 13 destinations. Going to create those computations. Going to run this. I'm not going to run this now. It takes about 5 minutes, but I encourage you to go and run it to see what happens. It's just building the graph once and then running 13,000 iterations on that, and you get your results there. So once you run this, it takes about 5 minutes on a machine, and you get your matrix layer like this. So output of this tool is like, you get output like this, and you can see this is a lot of edges, right? Because it's from every point to every point it's connected. Let me show you the attribute table of that. And the attribute table looks like this. From every origin ID, you can see this is the ID, the source ID is one of the addresses. It's computed 13 distances, and this is the total cost. And you can see there's an entry cost snapping to the network, routing on the network. This is in meters, what is the distance, and the exit cost, because even the destinations are not exactly on the network, so it computes the nearest, the straight line distance from the network to that road and adds that. So this is a total cost. And now you can see from each origin, which is the destination, and each of them, and you can visually see, okay, I can now see, oh, this is the lowest cost. So now for this address, facility ID 1 is the closest one. And since there are 13,000 features, I can't manually do all of that. So we'll filter out this layer and select only the minimum queries on that. Now, how do we do that? We have, there is many ways to approach this. One easy way, and that works in a processing toolbox, is just to apply a simple SQL query. And now the processing toolbox now has a processing tool that can apply arbitrary SQL queries on your vector layer. So now you can be part of a model and you can automate that. So I'm going to show you how to kind of select that. And what we're trying to do is just say, for each pair, select the pair that is a minimum distance. And that's easiest to do in SQL settings. So I'm going to just pick up this query and run this on this layer. So if I search for SQL, I get this new tool called execute SQL. And I can select the input. I want to run this on the distance matrix. And what's the query? And query is select origin destination. And this is the key part where it says select the minimum total cost. So select the pair, which is the minimum cost, group them by origin ID, and input one refers to the input we selected. And since this is also a vector layer, we say select the geometry as well. And then I can say, my output should not be just a table, but it should be a line layer. So I can select this here. So now I can run this, and it'll filter out and give me all the queries here. So now you can see from the results here, it is connected each point, address point, to the nearest hub, and the distance, the routing is along the network. And how can you tell? Look, compare it with our hub distance. So this was the straight line distance, and you can see the difference. Now these points, it doesn't connect here because the nearest hub is here. Interestingly, look at this part. First time I saw this results, I was like, this says something wrong, because you can see this point here. It's so close to this point, but it's connected here. Because if you look at the network path, because there's no path here, it has to go all the way like this here. And that is longer than the one here. So in I have a step-by-step instructions here. And if you can get the data set and the same routing here, and I show that at the end here, that you can see from this path, though this is so close, if you have to travel all along this end, this is 5 kilometers versus less than 5 kilometers to this facility. So it connects that, and that's a really useful analysis. So this is your exact analysis that you've done to find the nearest facility, and the output is just your ID of each address, ID of the facility, and then you got this. And now you can imagine the power of this analysis. In just 5 minutes in your desktop in open source software, you are able to find the closest facility of 1,000 points, and you can kind of use this for a whole bunch of interesting analysis. And this is also called kind of an allocation analysis, where you can say, what is the nearest fire station, what is the nearest hospital to each place, and so on and so forth. All right, so if you've finished the nearest facility analysis, I'm going to move on to the location allocation problem, and I'll show that next. But I'm going to pause for a second and take questions.
Yes, so we have some questions. Just a comment from Clemens Raffler, who's the author of the QNeat 3 plugin, who's busy watching. And he just said, I'm so excited to see QNeat 3 used in a live tutorial. I didn't imagine that it would ever get this far when I started the plugin as my personal Python hacking project in 2017. Thank you, Ujaval Gandhi. So just a vote of appreciation
for the wonderful plugin, and it's a really nice, and I have a few feature requests coming your way.
And then we have some questions from Deepak Gupta. I don't know how to pronounce your name properly, sorry. We do the same analysis. Can we do the same analysis for one origin to multiple destinations?
Sure, just flip the data that you choose as your origin and destination. I think it should work similarly, because it's a distance matrix, so it doesn't matter what you choose as your origin and destination. So yeah.
Okay, and then I'm apologizing to everybody for if I mispronounce your names, because some of them are quite difficult for me. So this one is from Tulalup Esther, and he or she wants to know what happens if the two locations defined do not fall on the road but away from it. Will the link be connected?
Yeah, so that is it just snaps to the nearest edge on the network. So that'll be a straight line distance to the nearest edge. And you can kind of see that in this screenshot, if I can just show that. So if you see here, the nearest road is here. This health facility is not connected. So there is just snaps it. There's a connection here, and that's your exit cost or entry cost that's added to your total cost, and that's what it is. And if you're doing this, it may also help just snapping your origin or destination to the nearest edge of the road, and you can snap it using whatever is appropriate for your use case, and just use that. So then there'll be zero entry and exit costs But right now, it's just a straight line distance that it uses.
Okay. Then the next question is from Andreas Neumann. He wants to know what units are used for the topology tolerance. I guess they're the map units, or?
Yeah, so that will be the layer units. So in the next example, I'm going to use a projected CRS, and that's in meters, so that'll be in meters. Here, this data set comes in as a lat-long EPSG 4326, so that is degrees. And I typically don't like to work in degrees because it's easier to imagine or have units which are in meters, but I just didn't want to add an additional step on this. All the network analysis anyway uses meters as units.
So can you just clarify, is it the layer units or the map canvas units? Okay, units, yeah. Thanks. And then the next one is from, again, I'm going to struggle with your name, Ewan O'Mahony. And they ask the default speed of in this OD tool, are they preset for modes? I don't completely understand the question. Maybe that makes sense to you.
Yeah, so if you looked at the tool, let me just open up the history. And when I ran this tool, sorry, let's go back to the. I'll just show you this again. And at the bottom, if you're in the advanced parameters, you see there's a default speed here. And the default speed is something that if your feed direction that you specify doesn't have any speeds, what speed should you consider? And so you can set it to whatever you want. And typically, you don't mix routing between different modes of travel. So maybe walking or driving, you have a separate graphs. And we'll see that when we do the last exercise, that you can actually build different graphs for different kind of modes, and you can set different speeds. So you can say the default speed of walking is 5 kilometers an hour, but default speed of driving might be 20 kilometers an hour. And that can change depending on the graph you build. So a single graph can serve a single mode of travel.
Okay, thank you. And then maybe the last question for this round is from Stelios Vitalis. And he asks, is there a way to penalize nodes, for example, to avoid many turns?
Not in this. I think the one way to. I think there's no node weights as of now, and I can see where the question might be useful. I read that UPS, the delivery company in US that delivers packages, they have actually in the routing software they have a penalty for a right turn where they actually encourage people to take left turns because they are free, and you can save a lot of time. So even if the destination is right there, they'll just say make 3 right turns instead of a single left turn. So I think those kind of logic can be built into a routing algorithm. The default tools here, I don't think there's a way to specify that, but as there are open source routing engines that I'll cover in the last part, and I can those can be configured to have those kind of advanced constraints.
Okay, thanks. There are a lot more questions coming in. I'll make a note of them all, and I don't know if we'll have time to go through them all, but as we get a chance, we'll just cover what we can.
Sure. Yeah, I'll cover the next bit, and then we'll take more. And if at the end, if we have time, we'll take all those questions.
Great.
All right. So moving on to another analysis, which is the location allocation analysis, and this time we are working with the data from city of Cape Town, and I'm just going to show their portal. For all my trainings and analysis, I use all open data. So a big shout out to all the agencies and folks who end up publishing the data openly. It really helps people like me and other citizens to use this data. So this is the city of Cape Town in South Africa. They have a really nice open data portal, and a lot of the city data is shared, and that's helped me develop this exercise. And that is a real world exercise which the cities or planning agencies can use. So I'll show you the setup a little bit. Let me just turn off all the layers. So this is the road network that the city has published. It's a city centerline network, and this is the greater Cape Town area. And they have, the problem they're trying to solve is that there are a bunch of waste management facilities, and those facilities accept waste from users. And here in city of Cape Town, they have this waste collection facilities where citizens can go and drop off facilities. So maybe not the household waste, but say garden waste, or maybe you have large furniture, you want to dump it. You don't dump it on the street, you go to this waste management facility and drop it off. And so they have a bunch of this facilities across the city. And then they have all this places where they collect waste. So each of this, the point represents the centroid of each small region, which is a waste management unit, which they call refuse collection beats. And these are, for example, this point represents the collection of group of houses here, which all have a waste pickup schedule, and they are all grouped to this point. So these points are the centroids of those polygons. And in this analysis, they represent the demand points, this is where citizens are, and they need to access these facilities. For this analysis, I'm going to assume that each point represents equal number of people or equal number of demand. But if you have data on how many houses are there and you want to group them, or if you have a demand weight assigned to it, you can use that in that. Right now, we are assuming that each of this point is an equal weighted thing. And here, in the stars are all the facilities, which are the waste drop-off facilities. And this is, again, from the Open Data Portal. These are the current facilities. And you can see they are scattered throughout the city. Mostly, you can see there are facilities close to a lot of areas, and you can find the one that's closest to you and drop your waste there. So, but you can see here that there is a large region here without any facilities. And maybe as a city planner, you are trying to build a new facility and say, where should I put a new facility, which is going to help citizens save time? And this is a quite large area. Where should we put? So I have created this 2 proposals. So you can see there's a proposal 1, which is, let's put a facility here and see if that is better or not. And the proposal 2 is a facility here. And just visually, you can't tell because we don't know which one will result in lesser travel time collectively for all the citizens. So these are the kind of analysis that is kind of choosing an optimal location that needs this network analysis. And you can do this with n number of facilities. You can have, these are in the location allocation terms, this is called your candidate facilities. You can have a list of candidate facilities, you have demand points, and then you can optimize. So I'm going to show you one flavor of the location allocation problem. We are minimizing the total cumulative travel cost. And we'll select the facility which is the least travel cost for all the citizens. There are many flavors of things you can do. You can say, I want to maximize, the number of people who can travel, or I can maximize the area I can reach. And, there are ways to do this. And once I go through the analysis, I'll explain where you can tweak and see what different kind of analysis you can do. So the setup, this is the setup. Now I have these 2 layers, proposal 1 and proposal 2, and which facility is ideal. So let's do the network analysis. The analysis is very similar to the last exercise. So I do my distance matrix between all my demand points to the proposal 1, demand points to proposal 2, and I get 2 distance matrices. And then I filter it out to the shortest path. And what I get, which I've already done, but you can kind of do this yourself. It's the exact same process as the last time we did. And then I have 2 allocations proposals. Okay. So actually, I already have those. So I'm going to remove this. So if I did the distance matrix from by using my destination as the proposed, using the proposed facility 1, including all the other existing facilities, I get this kind of graph where I can say for this point, now they can travel to this new facility. You can see there's no facility 2 here. It's just.
Okay, I'll just wait for the room to just confirm me back again. Okay, as I mentioned at the start, we had this sort of 1 hour cutoff. We should be back if somebody in the chat could just confirm that they can hear us again? Okay, we're good to go again. Thank you for your patience, everybody.
All right, so let's pick up where we left off. So here is the network analysis, the distance matrix results by considering the existing facilities and including the new facility one. And now I have got the network distances from each of these demand points to the facility. And this is what it visually looks like. But if I do the same analysis again and include only the existing facilities and the proposed facility number 2, this is what my allocation looks like. And you can see now that people here, there's no new facility 1 here, so they need to travel to this facility. And now I have these 2 competing proposals, and I have found what is the cumulative travel time for all of that, and I can select this one. Now, how do I compute the cumulative travel time? So this is just a layer. You can see this is just a layer where each point has a shortest distance. So I can just sum up the total distance, and that will be my cumulative distance. So there's this nice little tool QGIS has called statistical summary. I can just use that and say, pick the proposal 1 and show me the shortest distance summary. Maybe I'll divide it by 1,000 so I can show you the kilometers. So it's say the sum is 2,765 kilometers. So in total, if you assume 1 person per demand point, in total with the proposal 1, they need to travel 2,765 kilometers if they need to travel to reach the facility once. And if you know the number of people per node, you can just multiply that and use that here. So this is the proposal 1, 2,765. For proposal 2, if you see that one, it is 2,706. So it's a lesser travel time, and that means the proposal 2 would save more time for citizens compared to the proposal 1, and that means the proposal 2 is where you should build this new facility if you want to cumulatively save time for people. So this is one way to do this analysis. I've seen the analysis having constraints such as, people should not travel more than 5 kilometers. So then you start, you can filter out all the lengths which are greater than 5 kilometers, and then continue analysis that way. So you can kind of add this. There are, for example, if you use ArcGIS or ArcPro, they have the network analysis kind of packages this up in a nice tool where you can configure different things and it runs this. QGIS doesn't have that nice packaging, but all the underlying functionality is there, and you can kind of build on that. You can keep building a model, keep applying filters, and you should be able to arrive at the same kind of results in QGIS. And this is an example of just with 2 facilities, you can do this with multiple facilities as well. So I'm going to pause now and just take questions.
All right, thank you. So the first question is from someone who goes by the initials RK, and he wants to know, can we do nearest facility analysis from any tool inside the network analysis tool without using the QNeat plugin?
Right now, the default one doesn't have a distance matrix functionality. So we need to use this. If you were too keen to use that, you can use the built-in routing and then script that. And that essentially is the same what the plugin does, where it's just running the same underlying analysis functionality for each of the origin destination pairs.
Okay, thank you. And then Mohammed Kaladam is asking, he's wondering how to formulate the condition to solve for TLS, reaching for the shortest path with the consolidation of visiting specific points.
Oh, that's a route optimization, the traveling salesman problem. I'm assuming.
I guess so, yeah.
Yeah, so I think that I'm going to show an example of that, and that's a route optimization problem, and you can't do that in QGIS yet, but there is a way to do this. I'll show you at the end.
Okay, and then Tuomas Väisänen, sorry about your name pronunciation again, asked, it would be really nice if QGIS could use networks built elsewhere, for example, in Python tools like NetworkX or iGraph. Is there such a feature planned?
I'm not aware of able to use external networks, but I assume it will be useful to use that, because there's a growing number of network analysis library on the Python side, and NetworkX is great, and there's things like OSRM and stuff. And how I've used them, I'll show an example of how I use the library OSRM, which is a really powerful routing engine. within QGIS, you can do some, just build a little bit of processing script and connect to that and use it that way. So I use it that way, but I can see the value in having that as importing that graph and routing of that. But I don't know if that's planned. Maybe the developers in the chat can.
Yeah, we have some of the core developers in the chat stream as well, so maybe they can mention anything then about that there. And then Deepak Gupta is asking, can we differentiate the result based on the terrain conditions?
Yeah, so to do this on the terrain conditions, there are ways to do this. One way, which I've done recently, where you can actually have a DEM at the bottom, and you take your road network and sample DM at regular intervals. So it's every 10 meters you sample that, and for every edge you assign the average change in elevation. And so now you have an attribute which is, say, for this segment, the change in elevation is X amount, and that's a cost. So now you can do a routing, and this was a project where we were doing routing on bicycling. So the bicycling, if you're climbing uphill, it's a much harder route than a flat terrain. So we would want to do an optimal bicycle routing, and then the cost of the network was the elevation change. So you can kind of take the DEM, incorporate that, and use that as an attribute that you can now give as your cost. And then it will optimize to save that cost and give you a bike optimal route. Another way to do this would be to do a routing on the raster side, where you just say give 2 points on the raster and it'll find the optimal path by avoiding finding the least path for each pixel. And that's a routing on the raster side. We're talking about the vector side. So raster tools are separate, and we'll talk about the raster routing. They're typically used, for example, recently I had one of the students, she wanted to do routing along in the ocean, where it says I have 2 points in the ocean, find me the shortest path, but avoiding all the land, because she was tracking marine animals. And she ended up using the raster routing, where you just have a raster with the land and say avoid all the land and find the optimal path. So there are ways to do routing on the raster side, but this is completely different from the network. Those are not networks. Those are kind of raster grids where you can optimize costs.
Mm-hmm. Maybe there were some other questions, but I'll keep them for the next session. Just a couple of notes as well. We had some people joining from Mexico who woke up at 3 a.m. to watch your talk. So just greetings to Mauricio Marquez and Luca Bellani and okay.
Yeah.
Are you there still?
You dropped off. So
okay, we're back. I think we can continue.
Okay. So I'm going to do the last bit of problem, which is the service area analysis. And this is where the network analysis becomes really exciting for me, because now I'm going to show you a way to leverage a lot of the web services for doing routing, and a lot of the problems that people had. Well, how do I build my network? How do I clean the topology? All of that's go away. So now I'm going to show the problem that I'm going to show you is this is a metro station network. This is a city in South India called Kochi, and this is the Kochi metro line. This was a shout out to the team there, one of the first cities to really openly share the transit data in India. And this is from their open data portal, and they have the metro stops and the metro line here. And what I want to show you is I want to determine the service area of this metro network. What people in the city can access this metro, and is there a gap? If you're planning for a new station, where should we put it? And those kind of analysis. And typically, if you're considering a metro, you want it to be walkable. So we'll say, in what areas from the city people can walk to the station within 15 minutes and use that, and that'll be the service area. So just to kind of add context, I don't have any network. I'm not going to have any network data. This is all it is, but I want to do network analysis. And this is the case in many cities where, the cities either don't have this data, don't maintain it, or they don't share it. So if you're in such areas, how can you do network analysis? The great thing is we all have a really nice, routable, open database of the world, and that is the OpenStreetMap database. So there are services that allow you to do routing on top of OpenStreetMap database, and you don't need to download this data. All of this happens as a service. So first, I'm just going to add my a base map OSM. So this is just the tiles. So there's no data here. This is just the tiles just to give context to our analysis. And I'm going to use another plugin here. And this is, if people ask me what's my favorite plugin in QGIS, and this has to be this plugin called ORS Tools. ORS stands for Open Route Service. This is a university project. They offer a routing API built on OpenStreetMap network, and they offer it as a free service. They also have this nice little tool called ORS Tools, which again gives you processing tools to do network analysis on that. I want to quickly show you their website, Open Route Service. And this is the service that can do a lot of this analysis. They can do directions, isochrones, distance matrix, geocoding, POIs. They can also do optimization, the traveling salesman. So I'll tell you how to use this API for traveling salesman problem. But they can do all this problems, and you can go sign up for a free API key. And once you come to QGIS, you install your plugin, go here, go to settings, put in your key. And the key is required because since it's a free service, they want to limit the amount of load on the server. So you have certain rate limit, you can't send too many queries, and you have certain daily limits. But it works quite well for even within those limits. So once I install ORS tools, I have all these tools here. And you can see all the usual suspects. I have directions, I have distance matrix, I have isochrones. So if I wanted to do a distance matrix, now with some data, I don't even need a network. I can just say use OpenStreetMap network, and OpenStreetMap network data is, they've got a rich topology. It's called turn restrictions, lane restrictions, all this time restrictions, and the ORS tools will just use all of them and give you the really accurate routing based on that without even downloading data. So I'm going to show you this tool called isochrones. Isochrones, the word means the areas of equal time. Chron is time. So this is a tool where it can give you, for each point, it can give you how much far you can travel in a certain time or a distance. So I'm going to use this tool called isochrones from Layer. And you can see there's no network here. It says I'm just going to use Open Route Service, take my stops layer, get some unique ID, and the driving mode. So here, as I mentioned, there are different modes of travel, and there's a different graph for each of those. And you are specifying what graph you want to use. So I'm going to say I want to walking directions. And in 15 minutes, so the dimension is time or distance, I can say, show me all the areas of the city that are accessible by 15 minutes of walk from each of the stations. And look at what happens when I run. When I'm running it, it's just sending this query to this Open Route Service, and I'm getting the results back. There was no data that was downloaded. There was no analysis that ran on a computer, and that's why it's really fast. And out comes this polygons, and these are all the isochrones for each station. And you can see they are not buffers. They're not just plain buffers. They are actually along the network. So that's why, if you can see, there's a path around the river. You can't go very far. Here, if there's a road, you can actually travel much faster versus there's no road here. So now, in just a few seconds with no data of my own, I was able to run this. And this analysis can be done any part of the world. And that's the great thing about OpenStreetMap and services like Open Route Service that allow you to do this analysis. And if you want to do distance matrix, come here and run a distance matrix. No need to configure one ways and using your own CPU, just runs as a service. There are limitations. If you're running this on a data, there's a limit of 40 queries per minute. So that means if your layer has, say, 1,000 points and you run it, the tool will run after 40 queries. It'll say you have exceeded your quota. So don't worry. Don't stop your tool. Let it run. As 1 minute passes, it's going to send 40 more requests. and it's going to continue. So because of the rate limiting, the tool will have to wait for a certain time if you're sending a lot of data. And same case with other things. So it will still work. I've done this analysis up to thousands of points. You just have to wait for the rate limiting to comply with that. If you are doing this large-scale analysis, you can actually run Open Route Service in a Docker environment locally. There are also solutions like OSRM, which you can run locally and run a whole bunch of queries without this rate limiting. But if you just want to use this tool, this is really great free tool to use this kind of analysis. And there are other tools in the plugins. There's a plugin called QGIS, which uses the Here Maps API. But again, the Here Maps API has a commercial term in the terms of service. So you need to make sure you comply with those terms of service. This one is based on OpenStreetMap. You can actually use it commercially without any issues. So that's the last bit of analysis I want to show you. Next, I'm going to talk about what can you do with more advanced routing engines using Python, and how can you connect using QGIS. But this is the end of the demo for this part. Any quick question I can related to this I can take, and then I'll move on to the Python tools.
So there's just the one question from the Cardinal. He says, if we don't have candidate points to start, but need to find one, then theoretically I need to run the same with many random candidate points.
Yeah, I think that would be the way to do it. Typically, if you're doing this in a real world scenario, in a city, you typically you have a limited set of points. So you can't just put random points. So typically what you would do is, which is the empty land, and, or select the parcels that are vacant, and, put a centroid at those parcel centroids, and then run this kind of optimization analysis on that. So you usually start with a set of candidate points. It just doesn't work without a set of those.
Okay, that's it from the questions for now for this one.
All right, cool. So now I'm going to show you some examples of traveling salesman problem. We had this question on how to do traveling salesman problem. And also, I'm going to show you this routing engine called OSRM. So Project OSRM is the website. It's an open source routing machine. It's a really nice open source routing engine that can do a whole bunch of things. So it can do all this stuff we talked about. It can do isochrones, routing, all of that, and all based on OpenStreetMap data. So this is written in C++, but you can just run it within your own system and done it. So how I've used this in the past. One is a recent project where I want to show you that. And the link to this is in the resources section. So this is a project I worked on where I wanted to do travel time prediction using the OpenStreetMap data and also the Uber movement. So Uber has shared this data called Uber movement, where they share aggregated anonymized travel time data for all the cities they operate in. Really rich data set, one of my favorite big open data sets that you can use. And so one key thing that's missing from OpenStreetMap is the live traffic or historic traffic data. Especially in developing countries, there is no such information. So we combine this, take the Uber's historic data of travel times and combine the OpenStreetMap and figure out build a machine learning model to say which is the predicted travel time. So given if I start 5 p.m. on Tuesday from this point to this point, what is the travel time? And we got really good results compared to, say, commercial services like Google Maps. So how did we do this? One of the things we needed to do for training our machine learning model was we had all these points. We needed to compute about 50,000 origin destination pairs, and we needed to get a distance between those along the network. And we need to do it quickly for very different kind of models. So, what we ended up doing was running this OSRM server locally. So they have a Docker image. You install Docker locally, run this, and then you get this Docker running locally at this URL, and then you write a simple Python function which sends the request to that source lat long, destination lat long, the parameters, and it turns the full route along with the distance, and we use that. And this was for 40,000 coordinates. This takes like 5 minutes. it's a really fast local machine, and I have instructions on how to install and run this Docker image. Even if you've not used Docker before, I've had people run this successfully when you were never familiar with Docker, but just follow these instructions, you'll have it running. Another thing that you can do with OSRM is this something called route matching. So a common problem if you have a lot of the GPS tracks, if you collect GPS tracks, is that they don't snap to the road network. So this is say me on my bike collecting with GPS track, and I'm traveling on this road, but the road points are, because of the GPS errors, they're not in the right place. And if I want to compute the distance, or if you're a cab company trying to compute a fare, you don't want to use this noisy data. You want it, snap this points to the route. And it might seem a simple problem, but it's actually a complex problem, because where do I snap this point? Here, here, and that really depends on the points previously, the trajectory, and all of that. So OSRM actually has a nice function where you can say, take my GPS track and snap it to the OpenStreetMap network. And this is what I show in the blog post, how to just run OSRM service locally, just run these commands. And then, what I do is I write a simple processing script in QGIS. So I create a QGIS script, which now runs and gives you a tool like this, which says, where's your OSRM URL, which is an input vector layer of GPS points, and out comes a snapped polyline layer. And this is all because OSRM is doing the heavy lifting, doing the snapping, and we just get the results formatted as a QGIS vector layer and use that. So similarly, you can write some PyQGIS script to call OSRM and do this really sophisticated type of analysis using OSRM there. The last bit I want to show is let me just pull up it's a traveling salesman problem. Sorry about the background noise. If you're hearing, there's a construction going on here. It just started this morning, so I was caught off guard with that. All right, so in your deck, we'll add the link to this in the description. Tim has already sent you the link to this deck. There are resources here. So these are the step-by-step guides. So if I just show you this one, this is published on the QGIS tutorial site. You can download the data, follow the step-by-step, and you can replicate everything I showed today on your own. The OSRM is here, the links I showed you. The traveling salesman problem. So now, as I mentioned, this Open Route service provides you with this optimization API. And I teach a Python class where I teach how to use Open Route Service API and how to do this. So in this Intro to Python class, one of my participants, he ended up using this optimization API, and he built this example. And it's a kind of fun example. What he's trying to show is that how easy it is and how accessible it is to now do this route optimization. And he's saying that, oh, I have this task where I want to meet Ujaval, but I want to do this task. I want to FedEx a package, fill up my gas tank, do this, and I want to meet him in what order should I visit all these places so that I can have a most optimal route. And he, in this example, shows how to configure your API request. And at the end, you just run this, and you get this. You have all these points, and say, I want to go from here to here, but in what order should I visit? Should I visit here and here and here, or which is the least network cost? And then you do this analysis, and the Open Route Service API, Optimization API, will solve this traveling salesman problem for you, and you get this, output here, which is the optimal route. And the API is quite rich. It can specify how many vehicles you have, what is the capacity of each vehicle, what is the amount of things you are picking up at each destination. So if you think about a waste management thing, I have to collect waste, I have a fleet of 100 vehicles, I have this demand points, I know this area generates a lot of waste. How should I deploy them? In what order? Which vehicle should go where? This can solve that. But since the problem formulation is quite complex, and the output also is not straightforward, because in this case it's straightforward, but if you have this 100 vehicles, what should be the output? So I think that's why it is much more accessible using Python. But I have linked to the example here where you can say route automation using the Open Route service. You can look at the Python script and try to implement that. Google Maps, if you want to use Google Maps also provides an optimization service. They solve the traveling salesman problem using the Google Maps API. This is a commercial solution, but people often ask how to do this in a commercial setting. Maybe the routing data in the region they're working on is not as good, so they want to use a commercial service. So this is an example Google Maps has for solving the traveling salesman problem. And I want to conclude by showing you what are the tools available for other kind of networks. We mostly talked about road networks. I primarily work on the road transportation side, but if you're working on the water side, there's a nice QWater plugin. There's a new GIS water plugin. All of them use Postgres database and the PG routing engine to do water like pipeline management. There are a lot more different problems. You have valves and you have flows of water and all of that, but the PG routing engine can solve all of that. For fiber network, I've seen huge demand for people doing fiber laying network, and they want to optimize for that. So all of this you can do. I've done kind of a smaller version of this locally. Where I just built some Python scripts and use the built-in network tools. But there are this company provides a commercial plugin based on QGIS that can actually uses the underlying routing API to do fiber network planning. So again, check out those plugins if you're working on any of this space, and you can continue with that. So all right, that's all the content I had today. Thanks for watching us. We still have 5 minutes, so I can take more questions.
Ujaval, I will actually, because we've got the next stream starting in 5 minutes, so I actually think we need to stop now. We did manage to get through a lot of questions during the talk, and of course, you're a wonderfully friendly and available person. If people have more questions, they can surely contact you on your website.
And maybe you want to plug in the AMA. I'll be available in the AMA later today, so you can ask me more questions there.
So we can carry any questions over. Just a huge thank you from me. It's been an awesome tour de force of the QGIS network capabilities, and thanks to all the developers and contributors who made all those tools. Obviously, there's a lot of work gone into putting all that functionality in place in QGIS. So, and a great thank you to the audience. Been really participative, and it's really nice having all your feedback and questions during the session.
Thanks, Tim, for organizing the open day. It's been really fun. Thanks to the audience. Look forward to interacting with you more. I'll be available later today for the Ask Me Anything. So ask questions or email me. The email is on the website, and I'll be happy to answer any questions. Thank you.
All right. Thank you. Thank you, everybody. Bye-bye.